Apologies for the small room. The reason is the bigger ones are not available this time. So, brief introduction of Steve Campbell. He came here at some point in the distant past, I don't know, before I came here, to be an operator theorist, which he did for a while. And he turned to pseudo-inverses and linear algebra, and most of his career has been on differential algebraic equations, their analysis, numerical solution, and control. He's the author or editor of 10 books. He's had 18 PhD students, starting with a guy named Ken Clark. I was wondering what happened to him. Last time I saw him, he was doing day trading. Okay, anyway, 18 PhD students, 11 master's students. And in addition to this, he's an accomplished painter, as you can learn from his website. And he does a lot of fishing, snorkeling, diving, underwater photography, etc.
Thank you. Well, thanks for asking me to do this. It's actually kind of a difficult talk to figure out how to do because the audience is so varied and everything. I'd like to begin with a special thanks to a few of the colleagues that I've worked with. I'm not going to read all the names. And then there's some more. And then NCSU students of my own that I've worked with. And most of them are finished, and some are finishing very quickly. A number of other students, primarily in France, some in Germany, and some other places. And in planning this talk, I looked back at the other talks in this series to try to take some inspiration from. And the first one I went to was Eric Kaltoffin's. Okay? So I got curious about, he talked about this Google Scholar thing. So I went to Google Scholar. This was actually very depressing. Because, there's not much of a trend, but it looks like it's going down. Right? I think it's time for me to dive a little less and write some more papers or something. Okay. So what to talk about here? This is a really diverse audience, faculty, students, strangers. Who's this guy? What's going on? And also, as pointed out, I've worked in a number of different areas. And so I decided to focus on sort of, not necessarily completely what I'm doing at the moment, but kind of focus on one of the things that I've worked on that I think is a very important problem. And that's going to deal with numerical methods for optical control. So a brief preview of coming attractions is that optical control problems have been solved in industry for a long time now. They're very important. Direct transcription is a popular method that's used a lot. I'll explain why. And the other thing is, as a mathematician, we all believe in theory. And the theory for numerical methods for differential equations, optical control, it's used to guide the numerical solution, it's used to evaluate the answer, et cetera, et cetera. And a lot of times this works out really great. But what turns out to happen is that when you do direct transcription, our experience has shown that a lot of times the theory doesn't mean what you think it means. In fact, people will misinterpret the theory. And in fact, the theory seems to totally contradict computational practice. So SoxX is a large-scale industrial code that we've worked with for a while. And we're going to talk about that. And so one of the emphasis is going to be how there's this interplay where for these kind of methods, you actually have to go back and reinterpret the theory. So here's the outline of the talk. What on earth is a DAE? A little bit about direct transcription in comparison to a couple of the other options you have. A little bit of DAEs. 3 examples where the theory needs reinterpretation. First one is error can be good. I may not actually talk about that this one. We'll see how this goes. I'm terrible at predicting how long a talk will be. All I know is that we will finish on time, not after. Okay? What are good DAs? We'll definitely talk about, and estimating multipliers. And then maybe a couple comments about some of the things I'm interested in at this time. In case somebody wants to chat about that after. Now, if you're going to talk about, you need to talk about the game it is that you're interested in playing, the theme that you have. And so there's been a kind of a theme that's driven a lot of my research for some time, and that's certain principle. The less expertise you require of a user of an idea, the more widely the idea is used. Okay? Secondly, the more widely something is used, the greater impact it has. Right? So, on the other hand, if you're not going to assume much knowledge of the user, then you need to have a lot smarter software and theory and algorithms. Okay? Plus, you have to assume people are going to stick things in there that you didn't expect, and you'd like to know whether or not you can handle them and how to deal with them. So we've been interested in general purpose in quotes, software, and algorithms. They can be used by non-expert users. Translate that as an engineer with a master's. For tackling, or PhD, for tackling hard problems and other algorithms that trouble us. So that's been kind of the motivation. Make no claims with the ways of being successful. You do have a need for the theory and stuff. It gets used by the software. And you also need to provide guidance to users. So what about DAs? So many physical problems are modeled by a system of Odie East like this. This U, which will appear sometimes and sometimes not, is just going to be a function or a vector value function called the control. So this is a system of differential equations. When we're talking about a DAE, we're assuming that this Jacobian of f with respect to x prime is always singular. They have a lot of different names. Sometimes they're called singular differential equations, which is different than Hangman singularity. They're called descriptor systems, and I'll explain what that is in a minute. They're sometimes called differential algebraic equations, which you have to use parentheses if you're using Google, because algebraic differential equations are not the same as differential algebraic equations. Okay. Or equations in differential algebra. So, it's referred to as constraint, semi-state, that out. Really, you're talking about differential equations on some manifold, implicit. They are related to behavioral models, but it's not exactly identical. Why DAs? The fact is that most models, a lot of models initially come in as a DAs. So if you want to model an electric circuit, you've got a bunch of devices, you've got Kirchhoff's laws, you've got a bunch of equations. Okay? Classical mechanics, you got multiple bodies, you have a bunch of equations related to them, you have some stuff that relates. Or you have a system, and you have a subsystem, and this system, and this system, and then you start hooking them together with wires and stuff like this. And so you naturally tend to get these large, complex systems that don't look like the XDT equal f of x. It may not be possible to make them into an ODE in a global sense. It may not be practical. You may have sparsity losses if you go implicit. In a simulation, you can have one implicit model, and if you're going to try to get to an ODE, you may only get to one ODE under certain variable values, you get another ODE, other one, and you get to work with one model. As I mentioned, large-scale interconnected systems. Sometimes, in order to get a explicit model, you actually have to make model simplifying assumptions, and there's extra design flexibility. So there's a lot of reasons why people have wanted to do this for some time. Now, ODEs can be different from DAEs for a long time. A good friend of mine, Linda Petzel, and Bill Gare wrote a paper once called ODEs or DAEs or not ODEs. And there's a variety of reasons. One is not all initial conditions will lead to a solution. Solutions can depend on derivatives of the original equations, their smoothness issues. If you try to linearize in the obvious way, that may or may not be appropriate. It depends on what your structure is. You have certain constraints you may know. There's usually other higher hidden constraints that are on there. There may be loss of smoothness, there may not. Even if you have structure, if you want to use standard numerical methods like backwards differentiation, implicit undercuts, and some of these kind of things to get a numerical solution in your ODE, the numerical methods may fail or have reduced order. So here's one of my favorite simple academic examples. So here's a little DAE in x and y. Alpha is just a function of t, it's a coefficient. F of t and g of t you can think of as a couple of inputs, which you may know. So you can solve this problem, and the first thing you notice about it is it has one solution, right? So if your initial condition is not x of 0, y of 0, you don't have a solution at all. The second thing to notice about the solution is here this part involves the derivative of g, so it's actually differentiated, it has a differentiator in it. And another thing is it actually involves the derivative of one of the coefficients of the equation, so it can depend on it. So if you're looking at an DAE, we'll talk about the word index in a minute. If you're looking at one that's index is bigger than 1, then the derivatives are there. It's not a question about, where do you have them or not. The question is how and when do you compute with them? Where do you put them in? All right? I will comment that loosely speaking, the index is the number of differentiations needed to get an ODE out of it. There's several other kinds of index, especially for nonlinear systems. So if you took this system here and if you differentiated it once, like this equation, you could get this information. And if you did one more differentiation of these equations, you could produce an ODE. So this is the simple index. There's essentially two ways to approach a DAE numerically or analytically. One is you reduce it down to an ODE or an algebraic equation in some kind of submanifold, sometimes easy, sometimes hard. There are codes that do this. If you're not careful, you can lose information about constraints. You can generate an ODE whose solutions contain the DAE solutions. Then you have to worry about the additional dynamics that enter. This kind of thing has been done a long time. Of course, then they ran into problems sometimes with simulations doing bizarre things because of the extra dynamics. Essentially, two kinds of approaches. All right, so that's your DAE background. So we're going to talk about optimization and DAEs. And we're going to assume you haven't had Math 739, which is your loss. So you got some kind of function of the control, a scalar value function. Call that the cost. It could be energy, it could be fuel consumed, it could be the distance from a target. It could be how much money you spend. You've got the dynamics, which act as a constraint. And then you have another kind of constraints, which here I am actually including inequality constraints up here. And then you have these inequality constraints that are around. Now, these kind of inequality constraints that act on X and U throughout the time of it, they're present in most applications. For a long time, we worked with John Betts, who was at Boeing and now is a partner in applied mathematical analysis. And in industrial applications, you just almost always see these. In fact, it's not unusual. I mean, in some problems, you'll have dozens and dozens of these things running around. And these are often not related to the physics. And it turns out that when you look at DAEs, there's going to be certain structure to the equations. And as we'll see an example or two a little bit later, if these constraints come from physics, they generate forces and that links things together. But if these are just non-physical constraints in the sense they don't directly affect the dynamics, it turns to do all sorts of bizarre things to it numerically. So, it could be a requirement that you want to keep your temperature below 200. Don't go faster than 30 miles an hour or you'll lose your warranty. Avoid that rock, in a space mission or something. I will comment that this is my favorite rock. This is the Saturns Moon. I love this picture. If I would have asked you as a kid to draw a picture of a moon, how many would have drawn this? This world is really a wonderfully crazy and bizarre world. That's actually an actual photograph of one of the moons of Saturn. All right. That's just a cool picture. So the DAEs can occur. So DAEs are coming in several different ways. So the DAEs come in if the initial model is a DAE, so okay, that's fine. The second way they can come in is suppose that you are doing a simple enough problem that your model was an ODE. Okay, that's quite possible. But you have these path constraints. Well, when those constraints come active, then you've got a DAE anyway. So for example, if this is a velocity constraint, then the dA index will be at least 2. If it's a position constraint goes active, then this becomes at least index 3. And in fact, if you have constraints and variables for which this equation doesn't involve a control, then the index gets bigger than 3. So you can, when these constraints go active, particularly if they don't come with structure, all sorts of things can happen. Another thing that happens is even if you start with an ODE, even if you don't have this stuff, the necessary equations themselves that come out of Pontryagin principle are always a dA when you think of the state and multiplier. All right, so the index of an inequality constraint, well, that's the index of the dA that results in the constraint is active. And if you want to think about classical numerical methods for DAEs, such as implicit Roget-Kata's, BDF, and some of that kind of stuff, they all require some assumptions to work. One is they only work for certain systems with certain structure. Secondly, they don't work for high index. And thirdly, none converge if the index is bigger than 3. And a lot of them aren't too happy if it's equal to 3. Keep it. So this is the theory is telling us this. And when I say don't converge, they literally go up and don't give you an answer. Now, this has been talking about DAEs and numerical solutions. What about optimal control? So let's face it, computers do, symbolic algebra, people may disagree, maybe not. But all optimal control solution procedures have to convert the problem into a finite dimension. And, well, I'll make up the number 3. Seems like a popular number. So 3 kind of general approaches. You have indirect methods, and you can sort of think of them as optimize and then discretize. So you could take the necessary conditions, which are a boundary value problem. You discretize that to approximate the necessary conditions, and you try to solve it. You can think of having some functional analytic minimization type algorithm in terms of operators and whatnot, and you can try to approximate the operators. It's important to note that, for instance, if you're trying to do a boundary value problem by multiple shooting or something, then you've got to integrate these constraint dynamics. Another possibility is you parameterize just the control function, you evaluate the cost, and then you call some minimizer that hopefully is better than F-min convolution. Well, F-min convolution. So, if you're going to do this, you evaluate the cost by integrating the dynamics. In any of these situations where, in fact, you are integrating the dynamics, all right, then the classical DAE theory applies in terms of what converges, order of convergence, and things like that. But transcription is a little bit different thing. It's not obvious at the front that it's different, but it turns out that it actually changes what happens. So what is direct transcription? It's the I don't want to think too hard way of looking at the problem at the start, but then to do it gets complicated. So what you do is you discretize everything in sight. You discretize your differential equation, you discretize your control, you discretize everything, and then you get this great big fat nonlinear programming problem, and then you solve this finite dimensional nonlinear programming. The advantage is, for one thing, you don't form the necessary conditions of the original problem. Right? You just don't. You discretize it, you solve this. This is definitely good. Okay? I can easily show you lots of problems where the necessary conditions, the multipliers chatter on and off numerous constraints. They're not even defined some places. It may be hard to prove the solution is optimal. That appears. However, what is the purpose of doing this? Is you're trying to get a good answer that's better than the customer, that gets them a promotion and you another problem to solve. Okay? And it tends to be good in practice. And I'll explain why. So here's the code. This was originally developed at Boeing, and since then it's been migrated along with some other stuff to this company Applied Mathematical Analysis. It's been extended, there's extra features been added to it, and so it's now called SoxX. And the way it works is the user gives it the problem. The user can give an initial time grid to do the discretization on. If the user doesn't want to, there's a default. Then the software discretizes the dynamics, solves a large sparse NLP. There's actually two choices here, barrier methods or SQP. Evaluates the answer, automatically generates finer uneven messages, solves NLP, and continues. Okay. It terminates upon a certain error tolerances. The error tolerances are in integrating the dynamics and satisfying the constraints. So what happens when this stops? When this stops, you don't know whether or not you have an optimal solution of the original control. What you do know is if you take the control and stick it in the process, the cost of doing that is your computed cost. Because you're making sure that you resolve the dynamics well. So if you get an answer and you say, this is giving me 50% better than we had before, you know you'll do 50% better than we had before, assuming the models you're working with. Okay. This word integrating dynamics, we're going to take with a grain of salt, and I think I'll come in. So SoxX primarily uses two discretization schemes. There's some other ones in there, but these are the two. So the default is on an initial coarse mass. It uses the trapezoid rule, which is a second order implicit undercutter method. So if I had just x prime equal f of tx, it would look like this. Then after two iterations, it switches over and uses the Hermite-Simpson's, which is a fourth order method. Both are implicit undercutter methods. It does this, by the way, because in the NLP problem, every one of the equations defining your discretization is now a constraint that has to be solved. And as you can imagine, a fourth order method, Runge-Kutta, has a lot more equations, and it tends to be a little bit more nonlinear and stuff. And it's actually easier to get feasibility for this on a coarse grid than the other ones. So this just helps it get started. Usually now, the developers assumed that the original DAE was a semi-explicit index 1 and x. So when people wrote SoxX, they originally thought this. And so the assumption was that the partial G with respect to, that should be a comma, is invertible. And given you, this will be the next one. SoxX is viewed as a collocation. Trapezoid and Hermite-Simpson are equivalent to 2 and 3 stage Lovato 3A methods. You don't even have to worry about that, what that means. The important thing is that for index 3 DAEs, neither one of those methods converge. By that I mean you take any index 3 problem, you apply those two integrators to it, and your answer will blow. All right, they go totally unstable. It's important to keep. So the standard numerical analysis theory is based on what the user thinks of a control. So as I just pointed out, if when we talk about it before, you say, well, given a U, you evaluate the cost, and you care about whether this is an index 1 DAE in terms of x. And this, in fact, is what is done in control parameterization. If you want to solve this with control parameterization, unless you're really lucky, you've got to assume that this is index 1 and 2. However, direct transcription doesn't do that, actually. It turns out that in the discretization, all the algebraic variables are treated the same. So in terms of this problem here, x2 is never differentiated. So really, x2 and u, this distinction is something that's in your head as the user. Software doesn't see it. x2 and u are two variables that are not differentiated. So here's a simple little example that just cooked up for academics. So we have this cost. we have this equation here with a bunch of variables in it. The f's are just known fixed functions. And you've got some initial conditions. So if you think of, if you look at this problem, z1, z2, and z3 are differential variables. z4 and z5 are algebraic variables. Now suppose that you came into this problem thinking that z5 was the control. If you think of z5 as a control and you're going to put it in there, and you look at this DAE, it's actually index 4 in the remaining variables. Indirect, shooting, control parameterization, all. However, SoxX solves it with no problems. So if I set qi equal to 1, that's the weight there for all the i's, it solves it without any problems at all. Traditional theory requires the cost function to be positive definite with respect to the control if you don't have some sort of constraints acting on. If you set q5 and q3 equal to 0, doesn't affect the accuracy of the solution at all. And those are the coefficients of what you're calling the control. If you exclude z4 from the cost, then in fact things go bad. So what's happening? You may have reasons for what you think the control is. They can be perfectly good reasons. The fact is, the numerics do not care. As long as there is some choice of control, often some control in some other coordinate system which you may not know about, which would make the an index 1 DAE, then in fact the code works. Right? So it's not important that your way of looking at it is index 1, but rather that there exists a way. So this has a certain consequence. So if you're going to regularize a constrained control problem, you're told to add, weight on the control variable or something. In fact, if you don't know what's going on, the best thing to do is to add a small regularizing cost on all of the algebraic variables. So let's look at a little physical example. This is less relevant than it used to be, as I'll explain why. So here's a typical vanilla constrained mechanics problems. This just says v is the velocity, and this is the second order equation. You have a physical constraint, g of xt, that will generate a force. It looks like this. So this is a typical constrained mechanics type of problem that looks like this, and lambda can be considered as a generalized force. All right? And let's suppose we want to minimize the cost. That looks like this. Now, here's the control problem we're going to look at. We're going to allow for the possibility that lambda is up in here. And we got a control variable floating around. And we're going to actually put the control also down in this constraint. So you can actually think of this as a constraint, but it's being moved by the action of your controller. And this in turn generates a force in what's going on. This is a index 3 DAE. So if I think of U as my control, this is an index 3 problem. If I consider lambda as the control and G sub U is invertible, then actually the DAE is index 3. So the typical way people would look at this is they would think of U as the control, and they would say I've got an index 3 DAE. Now, the designer is not likely to think of lambda as the control, but the fact that it is a theoretically possible control totally changes whether or not you can solve the problem with direct transcription. So we're going to look at an application. This application used to be of great importance to the state of North Carolina. I have doubts whether it will be useful for this year. With luck, sometime in the next few years, it will be useful. The hockey puck. Right? So what we have here is we have some, typical dynamics. You get simple linear friction. We won't worry about whether that's right for ice or not. And here we have a straight constraint. That's the hockey stick. Okay? And your goal is to move the hockey stick and push an object, a puck, which is located at point xy, which of course is at the contact. B and C are determining the location and orientation of your pushing surface. Right? And your object is to push the object over close to the origin. Think of that as maybe being a little gap in the 5 spot of the goalie. And try to do it, though, minimizing the cost and so on. Now understand that our control variable here is BC, the orientation of the stick. This is an index 3 problem. Trapezoid and Simpson don't converge as integrators, but that's all right, they solve the problem. This is a graphical representation, so we're starting here and with a certain given orientation. And of course, you know, as a hockey stick, you go like that, and if you want to move, just lift it and go back up. So we did not model the lift. We assumed that that little lift you can do when you're dribbling is right. I never could dribble, but that's why I played defense. Hockey was the only sport that made sense to me as a kid. If I tried playing football, I'm slow. I can't catch. So you play blocking back, which means you stand back there and wait for their absolutely biggest, strongest player to go up and run into you after the play's over. Okay, that didn't make sense. Basketball, the guy's got the ball. You're not supposed to touch him. That didn't make sense. Hockey, he has it, you go get it. This I understood. So I played defense on the club. Anyway, so here's the actual solution. The point of it being, though, is that in this type of mechanics type problem, is we're getting nice solutions. We understand what happens, but not if we just apply it. So the one advantage. So another case where the theory doesn't quite work right. This is a little bit more numerically important. So one advantage of direct transcription is you don't need to form the necessary conditions. So you don't need to worry about the continuous time adjoint multipliers, which might not be continuous functions. You may not even need to find. But sometimes you do want them. There are reasons that you won't do want them for sensitivity reasons or things like this. And also even for control. Hager, who was in Florida at that time, has done a lot of work in this area. He showed that if you get good enough multiplier estimates, you can actually use that to upgrade your control estimates. So let's give an example of the necessary conditions. There's our little math, 731. So you want to minimize some sort of integral function of the cost. You've got this. We don't have any inequality constraints or anything like that. You've got Odie dynamics. You've got initial condition. And what the necessary conditions look like are this. This is if you don't have bounds on the state of control, and you assume that this thing is appropriate convexity in U or something. So, but the point about this is notice this is a boundary value problem, right? Differential equation x, differential equation lambda, and then you get this thing here, which is an algebraic constraint. So it's a boundary value. So you may want to estimate these continuous multipliers. Now, suppose that x star, u star are the theoretical multipliers that you'd like to have. Or from the optimal solution, lambda star is the continuous multiplier in necessary conditions. Now, if I'm discretizing things, and I go in and do all this, direct transcription gives me discrete values of the state, discrete values of control, value of the cost. But in the NLP problem that's solved, one gets discrete lambdas. And a natural question to ask is, do these discrete lambdas estimate the continuous ones? In fact, if you do want to prove that your discretization does something really good and optimal, you very frequently try to link these discrete multipliers in with the continuous ones. So do they estimate the continuous ones? So Hager looked at a whole bunch of implicit limit cutting methods, really nice bit of work. Given the order of my numerical method as an integrator, he said you get full order in the state, full order in the multiplier, and full order in the control if the control is found from the multiplier. Now, trapezoid meets Hager's assumption. Okay? So trapezoid should be second order in the state, and trapezoid multipliers should give a second order estimate at grid points. However, you can run a zillion computational tests, and they show that the adjoint variables are first order, not second order. Nothing wrong with this theory, it's a beautiful thing. However, when you actually run this, you don't get what it says. That's the kind of question. It turns out that Hager's analysis is based on the typical kind of way you think of Runge-Kutta methods. So for instance, trapezoid method using what's called the Butcher array, which is kind of standard ways of writing the Runge-Kutta methods, looks like this. SoxX actually used a compressed version of these equations. Mathematically set equivalent set of equations. Hager actually proved that for this and a lot of other Runge-Kutta methods, there were several ways to implement them. And he showed that you got the same accuracy in the states and the same accuracy in the control, no matter how you implemented your Runge-Kutta. You notice something's missing from the list. Turns out there was a reason he didn't prove that they did the same for the multipliers because. Okay. So here's a specific. He doesn't take a complicated example to do this. So it turns out that we went in, and this work here, by the way, was done with Van Engelsen some time ago. And it turns out that for multipliers, it matters the specific details of how you implement that Runge-Kutta. And there's lots of different ways. There's compressed ways, uncompressed ways, how you mix these equations. And even though the different ways are mathematically equivalent, even though they give you the same state solutions and the same control solutions, in fact, they'll give you different multiplier estimates. Hermite-Simpson's got a lot of different ways. That's a lot of formulas and betas and stuff. For Hermite-Simpson, Hager says you should get third order convergence with the state multiplier and post-computer control. It turns out that we see fourth order in the state, second order in the control, and second order in the multipliers at midpoints. But not at the... So it turns out you can get better at it. You see that there's all kinds of different order conditions that goes on here. In fact, we are able to get second order at the grid points, but you need to use an estimate like this rather than using the standard estimate. And there's theory to back it. So this is another example where the theory looks nice, but in the numerical methods, you have to go ahead. So summary up to this point, direct transcription is a very useful method because you can use it to attack very, very complex problems. However, traditional theory and practice are sometimes different. You cannot just apply the standard numerical theory, you have to go in and work things out. We're having several areas of current research extending the types of problems that we solve and what we better guidance to use them. I might comment briefly on that, the other one. Another way in which they're different is there's a question is how we're able to get some of these, remember, the numerical methods weren't supposed to be able to converge. Even in the case where the problem sometimes is index 3, we're still getting solutions. And there's a question of how that's possible. And you have to understand the difference. If you put in an integrator, right, you start here, you propagate your information, you propagate your information, you propagate your information. And that propagation is up to basically your round-off error. In a direct transcription, you have all those discrete equations, and they're being fed to an NLP program. And then the NLP is solving every one of those equations to a certain accuracy. That means the NLP solver could add a little extra error here, a little extra error there. And you can actually show what happens is that You can think of an unstable method as being one where a small error propagates and gets big. But it's also a method where a small change can knock out a big error. And if you go in and look, and that's exactly what the optimizer does. It makes little perturbations which then perpetuate it and knock out the large oscillations and produce a good solution. It's a very different kind. Okay, what am I doing now? We're not going to give a whole nother talk, but in case somebody wants to talk about that. So we got 2 or 3 things going on. We're looking at numerical problems. This is kind of a continuation of what we're talking about, but we're looking at problems with state and control delays. This is joint work with Karina Thompson and John Betts. And this turns out to be kind of an interesting, because one of the issues we're dealing with is one of the favorite things numerical people like to use is you take a uniform grid and do your analysis. We have a certain class of problems in which you can solve beautifully with uniform grids. You put in a non-uniform grid and you get problems. And so your analysis has to intrinsically deal with non-uniform grids. Which Promethean will do eventually. Right, Promethean? But that's going to be, that's fun stuff. And another thing we're doing, which is more classical control, is we have systems of DAEs, and we're constructing observers for time-varying systems, and observers are differential equations that approximate other differential equations. And that gets to use lots of classical control theory and DA theory. And then actually there's motivations for this dealing with fault detection and some related things. Jason Scott, who started working with me more recently, we're looking at systems modeled by DAEs, and we're doing failure detection and fault detection. There's several ways to do this. The initial way we're doing is actually observer-based and another thing. And then actually active fault detection, which is kind of control problem. You're trying to stick as little into a system as possible and be able to tell it's not working right without causing too much problems. So this is systems of delays, and that's a major thing we're working on. I will comment that with direct transcription on delays, we really would like to avoid. Whether they're neutral, whether they're retarded or advanced doesn't care for us. We solve retarded and advanced the same. Mixed is not so bad. There's some issues with neutral that we're trying to sort out at the minute. We've made progress, but there's a lot of interesting problems here. And it's requiring some modification of how we understand these things. Thank you for coming. Happy to talk to you about this or anything else. I violated my first rule. I always tell my own students you should talk 1 minute before the end of the session, and then there's no time left for questions.
Thank you. Are there questions or comments for Steve?
Tim.
So, the last time I talked to you and John about this concept of virtual index wasn't floating around. When did you guys figure that out?
This came out actually, it came out of some time I spent in Germany with Multipliers. We were looking at some reformulation of control problems. It was starting to rear its head probably at the very end of the time as Anna was going out. But in terms of getting fully elucidated and understood, and understanding how often it occurred, that came up
here. So, because I'm ignorant, but for high index systems, it's hopeless.
Define how
4? Index 4?
what is hopeless?
To solve them.
So, okay. Another thing I didn't mention here is an interest of mine is developing software that can integrate any reasonable DAE. If the DAE is smooth, we can do it. There's a couple of different types of codes. But then basically, one of the ways to do it is you actually generate a larger ODE that contains it, and then you can also generate nonlinear projections to stay in the manifold, and you can do some of that stuff. And some of that with Carmen Arvella. So you actually have a code that can do it. The other thing that happens is it depends on the particular nature of the problem you're asking. Just integration, if you have a constraint that's going active as opposed to a constraint that always exists, optimizers always have this choice of going slightly off it. They can always play with it. And if there's something that's minimal, an optimizer likes to try to get there in some sense. And so if it can throw a little noise in that makes the answer closer to truth, it'll do it. So the optimization process itself can act as a regularization on these problems. But for higher index problems, yeah, a lot depends on if they're structured. I mean, you can get an index is not a property of a set of equations. It's a question of what you're doing from it and asking for it. You know, x prime equal f. Well, if I give you f and you want x, you integrate. If I give you x and you want f, you differentiate, okay? So there are some problems that are very high. I mean, I've seen chemical engineers solve index problems. You had a whole series of cracking towers, and you're trying to specify the output, but your control is way back here, so they got to work their way through a long chain of integrators. But then you have lots of other things you can do along the way to kind of stabilize them. It very depends on the structures. Yes.
Yeah. How's the relationship with the singular perturbation problem? Suppose I got epsilon x dot in front of algebraic equation. Then if you drop epsilon from algebraic.
Sure. So one of the earlier, some of the earliest work on if I did a little singular perturbations. So some of the earliest work dealing with DAEs actually looked at them that way. In fact, for a while there was a sub-community in the EE who viewed the DAE as the reduced problem in the singular perturbations problem. So the idea was you had an ODE, you had some fast dynamics, you assume that fast dynamics were, you set your epsilon equals 0, and then you had an ODE, or DAE. And that this was describing the reduced problem, the slow dynamics, okay? And that was done early on. However, they can do the both ways. I saw a funny paper once where they started with a really complex model, and they simplified it, and then they had a DAE, and then they did something, they went to a simpler model, and then it dropped into an ODE. And it was just, you know, so what depending on what they add and what not. But that is one place they occur. They do appear as the reduced order models. So in the simplest type singular perturbation problems look like this. And then you usually have to assume something about that matrix is stable or something. And so you're interested in these kind of problems, and then these kind of problems typically will have a solution that looks like this. Here's, let's make it a matrix. So they have this kind of nice slow part, and then there's this, like these fast transients. And so you set epsilon equals 0 and solve this problem, which is hopefully talking about this, and then you do some kind of an asymptotic expansion or something. So there are some links in that sense, but yeah. And anyways, a bunch of work about that connection right probably late 70s. Any other questions on this one?
Is that it? Okay, thank you.